Hello, welcome to NPTEL online certification course on Introduction to the Application of Artificial Intelligence to Robotics. Today we are going to talk about reinforcement learning. Okay, so it's a third principal type of the machine learning which we are going to see, and in this lecture we are going to see how reinforcement learning could be used in case of the manipulator grasping an object. Okay, so by the end of this lecture, you will be able to understand the fundamental of reinforcement learning. Then what are the core reinforcement learning components such as agents, environment, state, action, reward within the reinforcement learning loop, and then comprehend policies and value functions, model free Q learning, and apply Q learning to a practical problem. Okay, so this is how organize the content for this lecture, where we'll be initially seeing the introduction, and after seeing all the components of the reinforcement learning, I am going to talk about the exploration versus exploitation, and then the model based versus the model free approach, and the Q learning, reinforcement learning example, and gymnasium, and the example with a code. So, this is how we are going to see. Okay, so I introduced this concept during the first week of the course, where we have seen the introduction of AI, as well as at the beginning of the week on the machine learning topic. Okay, so just a quick recap of what we have learned about the machine learning till now. So it is basically classified as supervised learning and unsupervised learning. In case of supervised learning, we have the input output, okay, that is there, and the output are labeled, right. And in case of unsupervised learning, we have the input and there is no labeling over here. Okay, so output is not there and we don't have the labeling. The goal in the supervised learning is the mathematical mapping from input to output, whereas in the case of unsupervised learning, its goal is to finding the regularities or the pattern in the data. The reinforcement learning, which is the topic of today's discussion, it's a third branch of machine learning, where an agent learns to make decision, okay, by interacting with the environment. Okay, rather than being shown label examples of the correct answers, as we have seen in case of supervised learning. It is also called as learning with a critic. Okay, in order to distinguish it from the supervised learning, where basically we have the learning with a teacher. Okay, learning with a teacher, because we have an input and corresponding to that input we have the labeled output. Okay, so that is there, whereas learning with critic means that the system evaluates, okay, as we are going to see, and it awards or it penalizes. Okay, so based on that the decisions are taken. So that we are going to see further in detail. Okay, so what does the learning with a critic mean actually? Okay, so a critic differs from a teacher, and the primary difference are, in case of teacher, you see, provides guidance, right? That is, we have the labeled output data for every input, that we have seen already. Okay, whereas in case of critic one, it doesn't tell what to do. Okay, it only provides an evaluation of how well it has been performed. Okay, the teacher provides information in advance for the learning. Okay, whereas in case of critic, the feedback is typically scarce and delayed. Okay, only after end of action execution that is available. Okay, the teacher provides the final truth or the data set, whereas in case of reinforcement learning, agent must learn to use critic's feedback, okay, to generate its own internal value system for the intermediate state. Okay, so we can explain the concept of the reinforcement learning with this schematic figure, where we have an agent, okay, and we have an environment. Okay, so the agent you can consider here to be a mobile robot, and environment, let us take it to be a maze. Okay, so here the fundamental strategy is learning through the trial and error, okay, without the direct instruction. and here the agent only has the ability to take action and then find out after that if the action were good or bad, okay, on a critic's evaluation. For example, teaching a dog with a new trick, okay, if the dog follows a command, you give it a treat, okay, that is term of machine learning, we can say it as a positive reward, okay, and if it does not, it gets no reward or a minor penalty, okay. So let us begin with the anatomy of the reinforcement learning, okay. So the first component is the agent, okay. So agent is the learner or decision maker, as I said, it could be a mobile robot, okay, and that interacts with surrounding and takes action, okay. Then the environment, okay, environment is the surrounding in which the agent exists and operates, okay, it includes everything outside of the agent itself, okay. For example, I discussed in the previous slide, we have a mobile robot which could be called as an agent and a mage, okay, it could be called as the environment, okay, where the aim is to reach to a goal point, okay, from an entrance point, okay. Next term is the action, okay, it's basically a move or decision the agent can make in the environment, that is what we call as action, okay. So it could be say go up, go down, go left, go right, like that, okay. So action space is a basically set of all possible actions, okay, an agent can make in the environment, okay, at a given state. For example, as I said, right. So any action, it is going to be a member of your action space basically, right. And these actions could be say discrete one, like say you want to press a button, all right, or it could be a continuous one, such that steering a wheel at a specific angle, all right. So that could be there, okay. The next term is the observation, okay. So we observe the environment after taking the action, right. So how do we observe? We look at the state, okay. So the state gives you the complete description of the environment at a specific moment in time, okay. So it helps agent to perceive and identify its current situation. Then the reward, okay, it's basically the feedback. Here we are looking at some sort of numerical value, okay, that measures the success or failure of the agent's action and helps to determine how well it is done, okay. Then next is the loop. So you see the agent, that is the mobile robot, okay, looks at its observation, okay, of the current state of the environment, which is maze in this case, right. Now it chooses an action, that is the move direction, okay. This action causes state change, okay. So you have the st plus 1 state at time say t plus 1, okay, in the environment, and the environment returns a new observation. Naturally, when state has changed, observation is going to change. So the environment returns a new observation and a reward, which is points or penalty, okay, to the agent, and this cycle repeats until your task is complete, okay. So this way it completes the loop. So the sequence of action from the start to the terminal state is an episode or a trial. Next, let us look at a term called policy, okay, represented by pi. Now how does the agent select the best action for the current state, okay. Agent is taking an action. Now the question is that which is the best action, how the agent can select a best action, okay. So it serves as the brain, okay, which defines the agent behavior, okay, mapping the state of the environment to the action, okay. So we have mapping from the state of the environment, okay, to the action, all right. So that is there. Now a policy can be deterministic, okay. What is mean by deterministic? that is specifying a single exact action for a given state. Alright, that is what we call as the deterministic. Okay, or it could be a stochastic. Okay, so stochastic means we define a probability distribution, okay, that is pi as, that is the probability of choosing action A when the agent is at state S over all possible actions. So, we could have the on policy. Okay, so in on policy what happens? Algorithm evaluate and improve the same policy, okay, that the agent is currently using to explore the environment. So, that is there in the on policy, right. Whereas in case of off policy, so algorithms such as Q learning, which we are going to see in this lecture itself towards the end. Okay, so here algorithm learn the optimal policy, that is the best next action, regardless of the agent current policy, okay, or the exploration strategy. Okay, now let us look at what is the value of the policy. Okay, so the value of a policy, okay, is basically the expected cumulative reward, okay, that will be received while the agent follows the policy, starting from the state ST. Okay, now for the finite horizon, okay, the agent tries to maximize the reward. Okay, so here your value of policy will be basically summation of the rewards, okay, and this could be written in the short form like this, okay, and the finite horizon I value goes from 1 to a definite time, okay, whereas if you have the infinite horizon, then here the I value goes from 1 to infinite. That is what is called as the infinite horizon. And there is one more thing which is used in the infinite horizon, and that is these gamma values, which we also called as the discount rate or the discount factor. This gamma value is between 0 and 1, okay, less than equal to 0 and less than 1, okay. So, it is designed to make future rewards essentially worthless, okay, than at this instant. Alright, why so? Okay, because you see generally there is a time limit, okay, to solve the given task. For example, if I take the case of a mobile robot, I cannot ask the mobile robot to run forever, alright. So, that is there. If gamma is equal to 0, then we can understand from this expression. If your gamma becomes 0, then you have this reward only getting counted, okay, and for the others one it is going to make them 0. So, only the immediate reward counts, and as gamma approaches 1, rewards further in the future count more, and we say that agent becomes more far-sighted. Okay, so if gamma becomes 1 here, then you are going to have the contribution from all the rewards, as you can see from this expression. Okay, so next question is that whatever policy we have seen, is there an optimal policy? Okay, so while many policies may exist for a given environment, optimal policy refers to the policy that ensures an agent receives the highest possible expected cumulative reward over the long term, okay, starting from any given state. Alright, so the optimal policy is expressed like this for all value of the state ST, okay, alright. So, now you see in control, instead of working with the value of state, that is V ST, we prefer to work with the values of state action pair, okay, that is you have state and you have the action, and this is represented as Q. So, in control system we rather prefer working with Q rather than working with V. Now, your V denotes how good it is for the agent to be in a state ST, and the Q STAT actually denotes how good it is to perform action AT when in the state ST. So, in case of basically Q, we emphasize on the action. Okay. So, we define Q star STAT, okay, as the value that is the expected cumulative reward of action AT taken in state ST and then obeying the optimal policy afterward. The value of a state is equal to the value of the best possible action. Okay. So, this is how it can be expressed basically. So, this I am defining my optimal policy, okay, as maximum of Q star STAT. So, by seeing the previous slide, we can write this expression like this, and then I can further rewrite this expression by separating this RT plus 1 term, okay, here, and I am taking a gamma out, okay. So, and here I am changing this one basically, okay, it was T plus I, but since I am taking RT plus 1 here, so I am starting here with T plus I plus 1, okay. And this is what basically can be written in the compact form like this. And further, this we could write separately in the form of this one, okay, where this PST1 T plus 1 ST comma AT is basically probability that the next state will be ST plus 1 given the current state ST and the action AT. Okay. So, next important concept is the greedy selection. Okay. If the agent knows the optimal action value function, okay, say Q star, it can derive the optimal policy by choosing the action with the highest value in each state. Okay. There is an important equation which is used over here, that is called the Bellman equation, and it provides a recursive definition of for the optimal value of a state based on the expected immediate reward and the discounted value of the next state. Okay. So, this is the state value form for that. This is in fact the equation which we have seen in the previous slide. Okay. And in case of the action value form, this could be written like this. Okay. And how this has come? This has come basically, this is how we define the optimal state value, okay, written in terms of the Q star, okay, and this is what we derived in the last slide. So, if I substitute for V star ST here, then I can get this term, okay. So, it is this term basically, okay, and so this term is going to be equal to this one. Alright. So, this is how this is written in the form of the action value. So, here this term is basically reward at the next state, which is the immediate reward. This term is the probability of the next state taking action AT in state ST, and this value is the maximum optimal value. Now, once we have Q star value, we can define the policy as taking the action AT star which has highest value among all the Q star. Okay. So, what is this pi star? This is basically choose AT star where you get the Q star. And how do we get the Q star? It is basically the maximum value of this one, Q star STAT. Okay. Next important concept here is the exploration versus exploitation. You see, exploration, as the name indicates here, choosing untested or seemingly sub-potential actions to discover more information about the environment, which may reveal better in the long term strategies. Whereas exploitation means the agent selects the best known action based on the current value estimate. okay, to achieve the highest immediate reward. Now, the core challenge in reinforcement learning is the agent must balance this trade-off, whether it has to do the exploration or it has to do the exploitation. Okay, so balance has to be there. Okay, so learning too far in either direction leads to the failure. Okay, so what happens if we have too much exploitation? Okay, so the agent risk getting stuck in the suboptimal strategy. Okay, that is possible because it will never try new things that might be the better one if it follows the too much of exploitation. And if it follows too much of exploration, then naturally the agent fails to collect significant cumulative rewards, okay, as it considerably tests the random actions. Now, so the goal here is to find a balanced trade-off, okay, between gathering new information and utilizing the existing knowledge, getting new information that comes from the exploration and utilizing existing knowledge that comes from the exploitation, okay, to maximize the cumulative reward over the long term. Okay, next important concept is the model based versus model free. Okay, now you see, depending on whether the agent has access to a model, model essentially here I mean the mathematical representation of the environment dynamics. So, in case of model based learning, what we have, we completely know the environment model parameters, okay, whether it is in terms of the reward or it is in terms of the state, okay. Here no need for exploration, we can choose the optimal policy, okay, with the known data using dynamic programming techniques, and the examples are the value iteration and the policy iteration. The other approach is the model free learning. You see, here we do not have the perfect knowledge of the environment, reward or the transition functions. Now, so the agent must explore the environment, okay, to query the model and learn from its own interaction. It uses temporal difference algorithm that look at the difference between the current estimate of the value of a state, okay, and the discounted value of the next state and the reward received. An example of this is the Q learning, okay, which is an off policy, and the SARSA, which is the example of on policy. Okay, next let us look at what is Q learning. Okay, so you see, the Q learning is a model free temporal difference algorithm used in the reinforcement learning to find the optimal policy for an agent interacting with an environment. So, the Q learning algorithm comprises like this, okay. So, here basically it has part what actually happened and you have the old estimation, okay, that is what we expected, and that this is what we call as the temporal difference, the difference between that we multiply with a learning rate, okay, and then we add it up in the current state, and that is how we get the updated estimate, okay. So, we would like this Q hat to converge to its mean, okay. So, we gradually decrease the learning rate, okay, over time for the convergence. Now, it has been proven that the algorithm converges to the optimal Q star values. Okay, it is useful in realistic scenario where agent does not have perfect knowledge of the environment rewards or the state transition function. There this Q learning is very useful. We can write the pseudo code for the Q learning algorithm as indicated here, okay. So, basically this is the same expression which I discussed, okay, and this is done till we reach terminal state. Now, for exploration versus exploitation, we use epsilon greedy, and the value of epsilon greedy is between 0 and 1. 1 minus epsilon is actually tells the probability exploits, and epsilon is basically telling that your probability explores. Okay. Now, let us take an example to understand all these concepts. Okay. So, first I am going to discuss the example, and after that we are going to see how we can implement that with a code. So, the problem statement is that, say, train a robot to move from a starting position of end effector or gripper to an arbitrary target location in the 3D space, okay, so that it can grasp the object. So, we provide a target object location in the 3D space, right. So, we locate the gripper location and then the Q learning model over here, and through that the gripper reaches target, okay. So, this is our robot, and then it closes the gripper once it reaches the target, okay. Next, let us look at the gymnasium, alright. It is an open source Python library designed to provide standardized interface for the reinforcement learning environment. We have already seen skit-learn for the supervised and unsupervised learning in the previous lectures. Now, this gymnasium is a standard tool which enables researcher engineers to reproduce results that compare algorithms fairly. And to facilitate research and development RL, Gymnasium provide a wide variety of environment, okay, streamlined API and wrappers to interface with the environment, and the 4 key functions, that is make, environment reset, environment step, and the environment render. Okay. So, in robotics, Gymnasium combined with the Muzoko physics engine to model the realistic robot dynamics, contacts, and gravity to provide a realistic simulation environment for the robotic research. It also allows reinforcement learning agents to be trained and evaluated in a virtual setting before actual deployment on the physical robot, okay. So, that is the advantage, and it supports simulation to real transfer, okay, which serves as a complete platform for the robotic research pipeline. So, here are some of the animations which is for the pick and place, for the navigation, for the humanoid, as well as for the object manipulation. Okay. Now, let us see the example with the help of a code, okay. So, we install Gymnasium, Robotics, Muzoko and Matplotlib, okay. So, we use fetch reach dense V4 environment from Gymnasium Robotics, okay. So, a 7DF fetch robot arm with 2-fingered parallel gripper, and the task is to move the gripper to randomly placed target position in the 3D space. So, the action space is a 4D continuous vector, and this action space comprises of motion in the x, y, z direction and the gripper positions, okay, whether it is open or closed, okay. Each is given value either -1 or 1, okay, and then the reward is the minus of distance between the end effector and the target, okay, per step. So, reward is always negative here, and closer to 0 means that the better performance is going to be there. Alright, so this is how we do this. So, we have import Gymnasium library, we import Gymnasium Robotics, okay, here, then we import NumPy and we import Matplotlib, okay. So, then we register environment, okay. So, we load all the advanced robot arm physics model so that they are ready to use, and we use dot make basically this fetch reach dense V4. This creates the virtual world fetch reach, okay. Dense means the robot is given a mathematical score every frame based on how far from the target it is. So, this is how we configure, okay. So, we take nx, ny, nz is equal to 8. So, what does this mean? This means basically I am talking about the 3D space like Rubik's cube grid, where 8 blocks, it is a 8 block wide, okay, in x direction, 8 block deep in the y, and the 8 block tall in the z. So, it is something like this. You have the x, this is your x, this is your y here, and you have the z here, right. So, it is just like your Rubik's cube grid, alright. So, then we have the bin size here, Okay, it sets the physical size of each grid block, okay, 4 centimeter. Then number of actions here. So the robot has 6 discrete actions here. Okay, so it could move forward in the x direction, backward in the x direction, it could go left in the y and right in the y, and up z and down z. Okay, so these are the 6 discrete actions which it can have. And then we have the action map. Okay, the action map, as I discussed, map 6 discrete action with the robot input. Okay, so these are values here. Basically 0 means nothing is happening in that direction, and plus means say going in one direction positive, here say forward in case of x, and minus 1 means the backward. Okay, then we create the Q table. It is 8 cross 8 cross 8 grid basically. Okay, and then we can set the learning rate here, say 0.1, discount factor gamma 0.95, and epsilon exploration rate 0.5, which is 50%. Okay, and we define a function to translate the raw 3D physics into our 8 cross 8 cross 8 grid. Okay, so that is there. We calculate the error here. So desired goal minus the achieved goal. Okay, so that way we get the error, and here in the training we create the empty reward list, and we run the loop 5000 times. Okay, and then reset, basically return robot at the starting position. Okay, so we give the range 50 basically. Okay, it means that the exactly 50 steps are going to take place, okay, to touch the dot, that is going to be there, and rolls a random decimal between 0 and 1. If it is less than epsilon, say which starts at 0.5 and decays, the robot randomly picks a motion between 0 and 5. Okay, and if it is greater than epsilon, the robot looks at the Q table for the current grid state and pick the motion that has the highest mathematical score. The robot translates its chosen motion 0 to 5 into the 3D physics using the action map and steps forward in the simulation. Okay, the simulator gives back the new observation, the reward, and check if the robot won. Okay, that is the program has terminated or it ran out of time, which means that it has the truncated. And then we apply the Bellman equation for updating of the Q table. Here you can see that. Okay, and then we get the state, that is translate the new position into 8 cross 8 cross 8 grid block coordinate. We update the Q table, okay, using this equation we have seen previously, and update its current location variable as to the new location and add the reward. So that is what we do, and we break the loop if robot touch the dot, okay, or terminated or hit the 50 step limit. Okay, so the round is over. Append the total score to the rewards list for the grasping. Then we decase the epsilon by multiplying it by 0.998 here. So this is what we are doing. The robot explores slightly less and trusts its brain slightly more every single round. This is what is meaning of that, until it hits a hard limit of 0.05. And you see, every 500 episodes we print the average score of the last 100 episode and the current episode exploration rate. So you see, we are printing every 500 episodes, that we are doing. You have the average value here and you have the epsilon value over here. Okay, so next we write code to print the learning curve basically. Okay, so these are the code which could be written for the plotting purpose. So you see, we have the total reward here and the episodes. We go up to say 5000 episodes here, and you see that these rewards move closer to 0, okay, which essentially means that the robot end effector is reaching to the desired dot point, which I have been talking earlier. Okay, so as the total reward converges towards 0, it demonstrates that the Q learning algorithm successfully minimized the distance error and found an optimal reaching policy. Okay, so we could further improve the code by increasing the state space resolution. Okay. So, instead of 8 cross 8 cross 8 grid, we can say take the size of grid to be 12. We can increase the training time, that is more episodes we can take. We can upgrade to deep reinforcement learning, okay, that we can do, and we can activate the gripper. So, to summarize, you see, the reinforcement learning relies on an agent interaction with an environment and learning the optimal behavior based on delayed numerical reward signal. Okay, we choose an optimal policy. Okay, so we choose this optimal action where we get this Q star. Okay, so that we do, and of course Q learning we have seen, it's a powerful model free off policy algorithm that learns the value of taking a specific action in a specific state, okay, without needing the perfect model of the environment. Okay, so that is why it is called the model free. Okay, and we have shown here the example, we have shown also the implementation of the code. Okay, you can read for the further understanding Introduction to Machine Learning by Ethem Alpaidin. Okay, thank you.